Okay, so now recording. Let me share my screen. Okay, so this is the design and manufacturing lab refresher lecture, um, and we're going to walk through the first 5 steps of the engineering design process. As always, with the synchronous lectures, I like to start with a cartoon, and this one I think is particularly relevant to what we're going to talk about today. This is kind of a play on that meme that I'm sure you guys have seen, where it's like, what my friend does, or sorry, what my friend thinks I do, what my mom thinks I do, what my boss thinks I do, what my dog thinks I do, what I actually do, right? Except this one is, you're looking at a product which is meant to be some sort of swing attached to a tree, and it's how the customer explained it, how the project leader understood it, how the analyst designed it, how the programmer wrote it, and so forth. My favorite one is how the business consultant described it, right? Which is this, beautiful, comfy chair with this sort of glowing halo behind it. But what's particularly important for the context of today's discussion is the difference between the top left panel, which is how the customer explained what they wanted, and the bottom right panel, which is what the customer really needed. So we're going to talk a bit today about the customer needs statement in the design process, and the fact that the customer often does not know what the customer wants. And that affects the design process, because a lot of times you have to change the customer needs statement, as you're already in progress through the design process, and that, as we'll see, is bad if it has to happen. But invariably, it happens almost every time, because as you walk through the design process, you learn more things about the problem you're trying to solve, and those things inform the customer needs statement. And so it is as with everything in design, an iterative process. So anyway, um, we are going to start with just a couple of quick announcements. So the first is, there is going to be posted on Canvas later today, an honor lock practice quiz. And I should mention here as an aside, I have not had a chance to update Canvas. Before it was the just time, because my wife got in that car accident. But now it's, we had a couple of international students join the class, and I have had to basically freeze the Canvas site for 24 hours to allow those students to join without creating any problems in the software in the back end. So that's now resolved. The students have joined, so we're good to go. So I'm really glad that it's Friday, because I'm gonna jump in here right after class, and pretty much spend the entire weekend getting caught back up with Canvas. But I realize that I've not posted the week 2 content, nor have I posted the thermo content or the dynamics content or the DML content. So that will all go up, today and over the weekend, so that we get caught up. So I apologize for that, but it was beyond my control. So I wanted to just make sure that everything got squared away before I made any changes. Um, so the first thing that I'm going to do is to post an honor lock practice quiz, and I've got practice in quotes here for a reason. It will become available today, the 22nd, on Canvas as a quiz, and it'll be due at our regular, weekly interval of deadlines, 10 p.m. on Friday of next week. Um, there's going to be just 10 multiple choice questions, and those questions are all going to be derived from the teaching team intro videos, right? Those 60-second videos that I posted as content for the first week. And I'm going to be asking questions that are really simple, right? That just come right out of those videos. So, like, what's Jenna's favorite color? What did Christian do on the weekend? What's Sam's favorite hobby, like, that type of stuff. And so you guys should be able to power through those questions really quickly, because they're not technical. They're just, related to the teaching team. And I have 2 motivations here. So one is I would really like you to watch the videos, if you haven't already, just to get to know the people who are teaching the class. And then 2, I want to kick the tires on honor lock. I've used honor lock before in 4501, and I've discovered that the first time through, there are always problems with people having the wrong drivers, or using the wrong browser, or not having the login credentials required. And so I want to make sure that we solve all of those problems in a really low stakes, um, situation, so that when you take the real quizzes, which will be coming in the next couple of weeks, all of the auto lock issues are all sorted out. So it's going to be, again, 10 multiple choice questions drawn from those teaching team videos. You'll be able to watch the videos. I'll make sure that that function is enabled in honor lock as you're taking the quiz, and you guys should be able to knock this one out, probably 15-20 minutes. The quiz itself is worth only 1 point. I know it's not a lot, but if I made it worth 0, nobody would do it, right? So I want to make sure that everybody actually does this, so that we do this test run of honor lock. And again, what it does is just gives you and me also a low stakes opportunity to troubleshoot and practice using honor lock. And then the form of this quiz, a multiple choice, honor lock enabled Canvas quiz, is ultimately how we're going to deliver the 4 quizzes that happen later on in the class. So this will just sort of give you practice with that format. So that's one announcement. The second announcement is, I've posted on Canvas an assignment, again in air quotes, that's due today at 10 p.m. It's a 0-point assignment, and its title is Informed Consent Team Selection Study. And so what this is anytime researchers do experiments on live subjects, right? You guys are live subjects. Whether the experiments involve just surveys or observations or actual like medical procedures, we have to get approval from the university. And once we get that approval through the university's IRB, internal review board, then we have to get your consent as the participants being studied to use your data for any sort of external publication or communication. And so that's what this informed consent form is doing. It's just asking for your consent to use data from the study that we're running this semester on team selection and its effect on the design outcomes. So I don't know which sections are going to be randomized. I don't know which sections are going to receive which treatment, but one section is going to be random team selection for the major design project. One team is going to be, you get to pick your team members. And then the third section is going to be, we will do a skills survey, so an analysis, self-analysis of your skills, and then form teams based on people's self-reported skill sets. So those 3 different treatments will be assigned to the different sections, and we'll run the study just by looking at the final artifacts that come out of the major design team process and see if there is any effect by how the teams are formed in the beginning on what the outcomes are. So please, before 10 p.m. today, please review the informed consent document and either accept or decline participation in the study. What you are consenting to is allowing pedagogical researchers, so that's Dr. Nemi, who's running the study, to use data generated from our class in external publication. So that's the key thing, external publication. Regardless of whether you consent or not, the study is still going to run, and the results will still be analyzed and used to improve EML 4501. It's just the only thing that we cannot do without your consent is to communicate the results of the study externally to people outside of the university. And so I would really appreciate if you guys would please consent, because what that allows us to do then is start to write papers that get published in peer-reviewed journals and conferences that allow other people who teach design or large enrollment design classes to use what we learned through this study in their own team selection process. So it helps us make engineering education better for the overall community. And I just will reiterate, you guys will see this when you read the informed consent form. All of your information is kept confidential. There's no way to tie any individual in the class to any of the scores or the numbers that we generate. So your anonymity will be preserved. But nonetheless, we still need your consent before using the data in any sort of external publication. Okay, so any questions about either the honor lock practice quiz or the informed consent? Nope. Okay, cool. Then let's move on to the second item in the lecture today, which is just a quick description of attributes of engineering design problems, and then a description of good design versus poor design. So up until now, with the possible exception of DML and maybe a few of your well taught lab courses, you guys have been solving engineering science problems, not engineering design problems. Now, what do I mean by that? An engineering science problem is one where the problem statement is compact and well posed, like the questions that you get on exams or in textbook homework assignments. The problem has readily identifiable closure, which means there is a logical way to get from where you are to step one to step two to step three to the conclusion. And to solve the problem, you just have to go sort of stepwise through that process to get from where you are to the end. When you get to the end, that solution is unique. And the way that you usually know that you've got the answer solved correctly is you flip to the back of the book and the answer agrees with the one that you calculated. And so, aha, hallelujah, you've got the right answer. It's the one correct right answer, and you can move on. And then finally, the problem usually uses specialized knowledge, which is if you're solving a problem in a thermo class, you're using thermo knowledge. If you're solving a problem in a dynamics class, you're using dynamics knowledge. Very rarely do engineering science problems have sort of the multi-physics mixing of different subdisciplines in mechanical engineering required to solve them, right? So a great example of that is on Wednesday when we were solving the dynamics problem to figure out the equation for the spring in the flame piston. We had to go to thermo, right? We actually had to solve a thermo problem to get the spring expression for the dynamics problem, right? So that sort of multi-physics is typical in engineering design, very unusual for engineering science. By contrast, in 4501, you guys are going to be solving an engineering design problem. And for a lot of you, this is going to be painful. In my own experience as an undergrad student, I struggled with design to no end. I have kind of an ongoing battle with that's lasted for 20 years with my design instructor over the way that the class was taught because I had a really bad experience when I took the class, and it was not the instructor's fault. It was my own fault for not recognizing that I was solving a different type of problem. So I want to really articulate to you guys that there is a difference in 4501, and it's going to be uncomfortable, at least in the beginning. So we're solving design problems. What sets design problems apart from engineering science problems? Well, one, the problem statement is incomplete, ambiguous, and can be self-contradictory, right? So if I go back to the slide that I opened on, this top left panel is how the customer explained what they wanted, and this bottom right panel is what the customer really needed, right? And so that is manifest in the customer needs statement that's generated, the problem statement that's generated for the design engineers to work on. A lot of times, those customer needs statements are incomplete, ambiguous, or self-contradictory because the customer doesn't know what the customer wants a lot of times. So that's why those statements are ambiguous. Um, Design problems lack a readily identifiable closure. So there is no clear path from where you are now to the final result. And they require or they produce potentially multiple viable solutions. So as you guys will see when we get to the end of this class, there's going to be, probably 13 or 14 different teams that are all going to be simultaneously solving the same design problem based on the same set of customer needs. We are going to get 13 or 14 completely different solutions, right? That all represent viable ways to solve that problem, just different because they're weighting different features or attributes or things differently, and so different things are emphasized in those designs, and as a result the end product is different. So you never know, right, when you've solved an engineering design problem, if you've got the best solution or if just around the corner there's another better solution that you didn't pursue. You never know. So that's a unique attribute of these types of problems. And then finally, like I said before, they're multimodal, multidisciplinary. So you have to draw in information from all of the engineering subdisciplines, sometimes science, chemistry, math, physics, even biology, even economics, even social studies. So like for example, in the last semester, our customer was the UF Biofoundry, and the project was a microbioreactor where the students had to pretty quickly get up to speed with some basics in biology in order to solve that design problem, right? So completely outside of typical mechanical engineering experience. But so you have to collect that knowledge and integrate it and become knowledgeable in fields that are maybe outside of your area, and integrate those things together to solve design problems. Um, so design does two things. So it is a decision making process, but then it's also a communications process. And when I say communications, what I'm ultimately talking about is the communication from the customer through the design engineer to the fabricator. We would call them technicians or technologists. And so kind of a really, I think, nice way of thinking about what a design engineer does is they serve as a filter and a conduit between the customer and the technician. In that, if you handed the technician a customer needs statement, that technician would not know how to build the artifact that satisfies that need statement, right? That's what the design engineers do, and that's why we get paid quite an awful, good amount of money to translate customer needs into final artifacts. Um, so most essential design activity is built around production of that final artifact, and the way that we communicate what our design intentions are to our fabricators, our technologists or technicians, is through engineering drawings. And this is way more important now than it ever was before, because before you would have an integrated engineering company where everybody would be in the same building, right? So you'd have, and the management would be on the third floor, the engineering floor would be the second floor, and then the job shop and the assembly line would be on the first floor, and the engineers would freely flow from the third floor to the second floor to the first floor, basically communicating what the customer needs, based on the understanding of management, down to the technicians on almost a regular basis. Like, so when I started in industry, that's precisely how we did it, right? It was everybody was in the same building. But now most companies are multinational companies that exist over multiple different countries, multiple different time zones, multiple different cultures and languages. And so it's very possible that a design engineer could be producing a product in the United States for a customer in Europe with raw materials extracted from a country in Africa, and having the actual fabrication process in China with workers who don't speak English but instead speak Chinese because that's their native language, right? This globalization and the flattening of the earth, per Tom Friedman, is unprecedented, right? This is a modern occurrence that really has only been true for the past 20 or 25 years or so. So you guys live in a totally different world than even as recently as 2000 with respect to globalization. And so it's super important as you generate those drawings that communicate to the technician how to build the artifact that solves the customer need statement, that those drawings be understandable and intelligible, because in a lot of cases you create a drawing and that drawing just goes into some very big complex system, and the engineer and the technician never have an opportunity to actually speak to one another, right? So those drawings have to be right, or else the thing that gets built is wrong because there is no additional communication between the engineer and the technician other than those drawings. And so that's what I say in this final line here, is just that the drawing is the most used communication form between the designer and the fabricator. Um, okay, but so we do even more than that, right? So we do more than just solve design problems and create drawings that articulate those problems. We also perform engineering analysis, right? And this is why capstone design happens at the end of a 4 or 5 year mechanical and aero curriculum, is because we need you to be instilled with all of the skill sets from all of the different classes that you've taken up until now to really be able to tackle these types of problems. So design is an iterative decision making process where you're going to be synthesizing science, math, and engineering engineering, and then sometimes biology, economics, social science, into the transformation of resources from raw materials into the final artifacts that meet the stated objective. And to do that, you guys are going to have to perform engineering analysis, which consists of two pieces. So one is gathering data, and the other one is evaluating and synthesizing data into results. Gathering data used to be really hard, right? So even when I was a student, the internet was a new thing, and all of the information that we had came out of textbooks. Now, everything is up on Google, right? It's all up on the internet. And so gathering information is super simple now. But what's harder is the synthesis and the analysis, right? So is the information that you're getting accurate, correct, reliable? And how do you take that raw material, that raw information, and convert it into engineering analysis that solves the design problems required to realize the artifact that meets the customer needs? So that's basically everything that you guys have been doing for the last 3.5 years, is learning how to synthesize information into engineering analysis. Um, and so we apply that engineering analysis both to do the design, but then also to evaluate and check proposed design ideas before manufacturing. And a corollary to that is that a lot of subproblems in design are interconnected. So you might solve an engineering design problem for one subsystem only to discover that it affects the performance of a bunch of other subsystems in an overall system design. And so you have to change everything in response to changing one thing, because of course, design is iterative and interconnected, unlike engineering science problems. And so to make this point, even more salient, what I've got here is a chart that shows time on the x-axis in a design process and the cost to make a design change on the y-axis. And so as we walk through the design process, there's preliminary design, detailed design, production, and ultimately consumption by the end user. And as you can see, the cost to make a change increases first linearly and then exponentially as you get farther and farther and farther in the design process. And so it is incredibly important, in order to keep the cost down, to make design changes using your engineering analytical skills as early in the process as possible, right? If you're in the preliminary design phase and you make a design change, it costs very little. If you make a design change after production has started, you either have to stop the assembly line and scrap all of the work that's on the assembly line, or position technologists at the end of the assembly line. It's a process called rework, right? I'm sure you guys learned about in DML. You take the final finished product off of the assembly line, and then you have some group of people there actually making modifications after the part has come off of the assembly line to make it function correctly, right? You want to avoid that. It's very expensive. And then even worse is once you've got the product out in the market, if you find something wrong with it, you then have to recall it, right? So you have to pay for the users to ship it back to you. You have to rework it and you have to send it back out to them. It becomes even more expensive once it's out there in the market. And so we want to make every single intervention in the design process to finalize the product so that it works as expected as early in the design process as possible, which is what's represented here. So you guys have got a ton of tools that allow you to do that. So you've got all of your coursework, all of the skills and knowledge and experience that come from your courses. You've got your undergraduate research, if you've done that, internships, and then you also have a suite of tools that we provide that allow you to do those engineering analyses and finalize the design before you get to the production phase and making changes starts to become complex. So what I'm showing here is just a FEA, finite element analysis, image of the body of a car, basically the chassis of a car, undergoing loading as it's driving down the street. And so the purpose of this FEA is to highlight the high stress points in the chassis, which you can see are along the running board here on both sides of the car, and then also along the windshield enclosure. to avoid those being potential failure points when you build this thing for real. So we give you FEA. You guys will have SolidWorks to do your CAD with. You guys will have access to PDM so you can control your process flow. You'll have EduPack to do material selection. So a lot of tools are now at your disposal. And what's hard, right? The reason that engineers get paid a lot of money is because synthesizing all of those knowledge, all of those tools, and all that knowledge together is hard, right? It takes a lot of skill to do that, and so that's what you guys are preparing to do. Um, okay, so this is just a summary then of good design versus bad design, and a lot of this is common sense. But good design meets all requirements. Bad design does not. Good design works. Bad design works sometimes, but stops working after a short time. Good design is in budget. Bad design goes out of budget. Good design operates with little maintenance. Bad design requires frequent maintenance. Good design is safe. Bad design poses hazards to the users. And good design operates without any ethical dilemmas, whereas bad design raises ethical questions. And to give you just a quick example here, you guys might be familiar with the Ford Pinto example or the NASA Space Shuttle Challenger, where engineers knew in advance that those systems had the potential to fail and cause harm to the users, drivers in the case of the Ford Pinto and astronauts in the case of the Challenger. And those systems were allowed to run anyway, despite those risks. And people were hurt and people died as a result of those poor decisions and ultimately the bad design. And so that's what I mean by raises ethical questions in bad design. Um, okay, so here's an example of what I think is bad design. Can anybody tell me why this is a bad design from the user's perspective?
If you try to drink from it, it could spill on you. I don't want
Yeah,
to.
yeah, there you
Splatter
go.
marks.
Exactly. Yep, this is a well, to make matters worse, it's a porcelain cup, right? So this suggests not only that you should be drinking something, but you should put hot liquid in it, like coffee. And given where the handle is, you want to pick this thing up by the handle here on the right, and as you tip it towards your mouth, all of not all of the liquid, but some of the liquid is going to spill out onto your lap. And it would be one thing if it were cold, but this is hot coffee. You're going to get burned as the user if you try to use this the way that it was intended. So this is terrible design from almost all of these perspectives, right? Certainly raising hazards to the user and creating some ethical questions about I wanted to sell this thing because it's a cool shape and people buy it because it looks cool, but am I going to hurt people in the process by trying to make some money by selling a crummy design? So here, by contrast, is an example of a good design. This is the leverage freedom chair, which was invented by a colleague of mine, Professor Amos Winter at MIT. And the reason that I highlight this is because it won a number of design awards in its time. And also Professor Winter and I went to MIT at the same time. And we were actually in basically the equivalent of DML, the design and manufacturing course at MIT together, and competed against one another in the design competition. And he beat me soundly. And so that's why he's an MIT professor now. So anyway, I just wanted to sort of point that out because I know the inventor of this thing personally, but this is a wheelchair that's meant for rural and developing countries, rural villages and developing countries. And if you think about what a wheelchair does, well, it's basically manually powered transportation for a user that has lost the use of their legs for whatever reason. Um, and if you have a conventional wheelchair, there's two really big problems with it. One is that the wheelbase is too narrow. And so if you try to go over a bump or a rock or a hill or something like that, there's a non-trivial possibility that the wheelchair is going to tip over. And so Professor Amos added this long wheelbase here to prevent that tipping problem and moved the center of mass forward of the wheels so that there's support points on either side of the center of mass to prevent front and back tipping. And then the other innovation is adding these levers, these handles. And you can see here in the detail, they're actually connected to the wheels through a chain mechanism, like a bicycle pedal. But the clever thing is that in a normal wheelchair, the user doesn't isn't able to change gears, right? To change leverage. The only leverage that they can get is by grabbing the wheels with their hands and trying to push the wheels. Well, if you're driving over a soft uh, dirt or gravel surface in a rural environment, you might not have enough leverage to get your wheelchair moving. And so, what these levers do is allow the user to select the leverage that they want to apply to the wheels just by where they position their hands on the lever. So, the higher up you position your hands, the longer the lever arm and the more leverage you can produce in getting those wheels to turn. And so, it's basically a self-tuning transmission system where the user just reaches up higher and higher and higher to get more leverage as they're moving along on a road that might be hard to navigate with a conventional wheelchair. So this is an example of an incredibly good design, particularly appropriate design for a developing or a rural community type environment where the roads aren't necessarily paved like they are for our conventional wheelchairs. And so I just wanted to show this as another example. Okay, before I move on then to walk us through a couple steps in the design process, are there any questions about the attributes of design or what good design versus bad design is? Nope. Okay, so given no questions, let's move into a couple of steps in the engineering design process. Now, this is actually going to be part of sort of an ongoing presentation that's going to span over several different lectures. And in those lectures, I'm going to touch on all of the different steps of the formal engineering design process, at least as they pertain to 4501, right? So we're going to march from step 1 all the way through to step 11 in this class. And there are a lot of places where I'm going to give you a lecture on how to do a particular thing, right? Like down selection or quantifying metrics or detail design. And so I'm not going to talk about all of those things today, but what I do want to do is just walk through the first 5 steps of this process, which you guys have seen before, both in my introductory lecture and of course in DML. So the first step is to identify the problem. And so normally what happens when we identify the problem is we get together as the design engineers with all of the stakeholders. So the customers, the end users, management of our company, board of directors, and figure out what it is that we're actually trying to design, usually using mechanisms like focus groups, right? So you get a bunch of end users or customers together and you ask them a bunch of questions about how is this thing actually going to be used to extract what the customer needs statement ultimately needs to be. In this class, we've already written the customer needs statement for you because we've done this process already with the customer. This is typically in some cases, it's the longest step in the whole process, is to gather enough information to articulate a customer needs statement. So we won't do it in 4501. We're going to give you a pre-canned customer needs statement, but just be aware when you go out into engineering practice that that's probably something that you'll be asked to do, especially if you're a design engineer working at a smaller firm, to run focus groups and get feedback from customers. The other thing that the customer needs statement does, is it's a living document. Now, what do I mean by that? Well, the Constitution of the United States is a living document. Why? Because it can be amended, it can be changed to reflect whatever the current needs of the country are in terms of a federal governance. And a customer needs statement is the same way, right? So a customer needs statement can change as we move through the design process and better understand what the customer needs are relative to the science, engineering, mathematics, and other elements, patents, papers, standards that we discover as we go through the design process and learn more about it. So I do want to sort of preface the entire class by saying, even though we don't like the customer need to change because it forces us to kind of go back and redo some of the work that we've already done, invariably it does, right? This happens all the time in industry, and it has happened before in this class. So although I try to write a customer need statement that doesn't change, just be aware that it might. And don't look at that as an anomaly or something that's bad. It's just an example of what happens in the real world. And so good experience for you guys. And so the example that I want to give in a way is related to the reverse engineering report, but it's very slightly different in that I'm interested in, or was interested in, the see-through fire tube that I showed you guys a couple of pictures of here. And I probably mentioned this, but before I took the job at UF, I ran a company, a design company that made laboratory equipment for both K through 12 schools and for colleges. And one of the things that I was trying to make was a flame tube that could be instrumented with a temperature sensor that would actually tell you the temperature as a function of time, or the temperature as a function of pressure inside one of these transparent flame tubes. And just like you guys are going to have a customer for your major product, your major design product, I solved a lot of the problems for my company by becoming a customer for other universities, who needed customers for their capstone design projects. And so I engaged with a university, and I had a group of students who were working with me on this design problem of how to measure the temperature inside this flame tube. And so part of the customer needs statement that we developed in collaboration with the students, between me, my company, and this university was this. So this product must measure the temperature of gas inside a fire piston in the range between room temperature and auto ignition temperature of the char cloth, with an accuracy of at least plus or minus zero point 0.2 Kelvin. And that product must fit inside the fire piston, not disrupt its performance, and be affordable by K through 12 schools. So that was the ultimate end user, was K through 12 schools. So like a high school physics class, for example, would be an end user. Okay, so that was the customer needs statement. We now move on in this example to step number 2, which is to research the problem. When you guys begin to research the problem, what you're ultimately looking for, if you look back at this first design point, is this first decision point in the design process: does a solution exist? So that's really what you're looking for. Does this thing that solves the problem that's been articulated by the customer in the need statement already exist? And if so, hey, I just can apply that existing solution without having to go through this mammoth design process. I could solve the customer's problem right away with something that already exists. And so that's really what you're looking for. But typically, if a customer has gone to the point of hiring a design firm and paying design engineers to produce a new product, chances are that product does not exist yet on the market. And so several things sort of happen in parallel. So yes, okay, you're looking for a solution to the problem, but you're also educating yourself about how that system, or how that problem, is solved in other contexts. And so what we're really looking for, at least initially, are standards, patents, and papers that describe a solution to the problem or similar problems. In a lot of cases, those documents don't exist because we're trying to produce something new that's never been created before. And so in a lot of cases, you'll find more information in the popular literature, things like magazines, newspapers, blogs, YouTube, where people are sort of trying things out and experimenting with things. So if you cannot find standards, patents, and papers, it's okay to use magazines, newspapers, and blogs. But if you can find standards, patents, and papers, it's better to use those as references than things from the popular literature. The other thing that you're doing is becoming an expert. And when I say expert, I use this in quotes because there are people who devote their lives to solving these problems. And those are the guys who write the papers and do the research and get the patents. And I don't want you to become that type of expert where you've completely gone down the rabbit hole and are, the world's foremost expert in some tiny little aspect of your problem. No. You've actually got to be an engineer and solve the problem for the customer in a way that makes sense and that is useful. And so when I say expert, you're just becoming acquainted with the prior art that's been applied to try to solve this problem in a technical way. And then a lot of times, especially if your customer is not non-technical, you're the one who knows more about how this problem has been solved previously than your customer does. And so that's another benefit of doing the literature review, is that you do develop this expertise in that process. So going back to my problem of trying to instrument this transparent flame tube with a thermocouple so that we could get temperature as a function of time, we did not find any patents or papers on how to do that, right? At least not for a flame tube because the product does not exist. And so the students who I was working with ended up going into the academic literature and finding allied papers that solved a similar problem, although not the exact same problem. That similar problem was, how do you determine the temperature inside and a car engine, an automobile engine in real time, right? And you might need to know that if you are adjusting the spark timing or adjusting the compression or adjusting the air fuel mixture of the engine to correspond to different operating points, right? You want to operate an engine very differently in a cold environment than you do in a hot environment. And so you might need to know that temperature inside the piston cylinder apparatus as a function of time in order to tune the engine in real time to get the best performance out of the car. And so these guys found a number of papers on this topic. This one used a thermocouple mounted on a reciprocating piston to transmit data out of an engine block via microwaves while the engine was running. This one used a laser diagnostic technique where they actually drilled optical ports in the wall of the engine cylinder and then shot a laser through the combustion gases and used a process called laser induced phosphorescence to back out what the temperature is. But wait a minute, all of a sudden there's a problem here, right? So remember, I've described to you this idea that the stepwise process isn't necessarily linear. Something that you learn in the second step could very well inform what happens in a previous step. And so you might have to go back and change things, right? And in addition, as I've said before, the customer need statement is a living document. It might need to be changed based on what you learn later. So look at this. In my customer need statement, I said the product must fit inside the fire piston. But the students in their literature review found a situation where a laser fired through optical ports in the engine wall gave me that temperature information without putting any hardware inside the flame tube. And so, was this statement really necessary, given that there are options to detect that temperature without putting anything inside the flame tube? And so, this is a situation where, as a design engineer, you would actually have to go back to the customer and ask, in this case, must the product really fit inside the fire tube, given the existence of external temperature measurement techniques? Is there some reason that's compelling other than putting a sensor inside to measure the temperature directly that you might need this as part of the customer needs statement? And so we went through that process of kind of discussing why there might be other compelling reasons to leave this in the customer needs statement, and we ended up leaving it in there ultimately. um, Okay, so the next step then is to make that decision about whether or not a solution exists, yes or no. In the case of my temperature instrumented flame tube, no product existed on the market that did precisely that. And so we moved ahead in the process to step three, which is quantifying metrics. So this is going to depart a little bit from what you guys did in DML. In that in DML, I think you guys were allowed to use binary metrics. And in 4501, I do not want you to use binary metrics. And I'll describe what that is in a second. So every customer need has to be quantified, and it has to be quantified over a range. When I say avoid binary metrics, what I mean is you want to avoid quantitative metrics that are basically yes or no, right? Is it something or is it not something? And the best example of that is the same thing that we were talking about before. Does it fit inside a fire piston? Yes or no, right? Yes, then it qualifies. No, then it doesn't. Instead of describing something as yes or no fitting in a fire piston, you'd want to come up with a metric that was something like size of the sensor is small, right? And then decide whether it's small enough to fit. And you actually give more points in your down selection matrix and your weighting to solutions that are ever smaller, right? The smaller the solution, the better, because the less it interferes with the flame piston and the faster its temperature response. So that's what I mean by avoiding binary metrics. Now, there are four categories of customer needs, and we're going to talk about this. I have a whole lecture on quantifying metrics, and so I won't go into this in great detail, but there's four of them. So there's already quantitative, quantified by code or standard, quantified by engineering measurement or calculation, or customer needs that defy quantification. And I have techniques to develop numbers for all of these different types of customer needs. So for the customer need statement that I introduced to you guys for that temperature instrumented flame tube, these are the customer needs that came out of it. So the range of temperature from room temperature up to char cloth auto ignition, an accuracy of at least plus or minus 2 Kelvin, that the sensor must fit inside the fire piston, that the sensor not disrupt the performance of the piston, and that the cost be affordable by K through 12 schools. And then here I've overlaid um, each one of these different types of quantitative metrics onto the specific metrics that came out of my customer need statement. And then in this slide, I've quantified them, right? So each one of these needs is now quantified. So the low temperature is room temperature, which is 298 Kelvin or lower is better, right? So I give a value, units, and then a range or the desired trend. The high temperature range has to be at least as hot as the auto ignition temperature for fire cloth. So 729 Kelvin. By the way, I found that value on Wikipedia, but Wikipedia is not a verifiable source. And so I had to go back to the primary literature, which turned out to be a 1949 paper on the ignition temperatures of papers, plastic, papers, woods, and fabrics. And of course, if I can get to higher temperature measurements, that's better. The accuracy is already quantified, so I'm just going to take that right through from the customer needs statement into my quantitative metrics. Fits inside of the fire piston. Well, I want the longest dimension of the sensor. And of course, I want that longest dimension to be as short as possible. And that longest dimension cannot be longer than the dead volume of the piston. Otherwise, the piston is going to hit the sensor every time that I try to do an auto ignition, and that's going to cause failure. So that moves into the next one, which is to not disrupt the fire piston performance. And that turns into a time metric. And then ultimately, affordability by schools is a cost metric. So once I've got all those metrics quantified, then I move into concept generation. And I've got a whole presentation on concept generation. So I'm just going to describe the concepts that we came up with: thermocouples, thermistors, all temperature sensors, RTDs, infrared thermometers, mercury thermometers, and of course, my favorite, the telepathic demon. And then I took each one of these concepts that I generated through a brainstorming process and used the quantitative metrics that I had defined previously and put in values for each one of those possible concepts. So you can see here a list of the lower temperature, upper temperature, accuracy, size, response time, and cost for each one of those concepts. And I had to look up those values. I had to do some engineering calculations to quantify them. But ultimately, I was able to come up with a number for every single one of those concepts. And then we eliminated impossible concepts, which, as you probably guessed, was the telepathic demon. When you eliminate impossible concepts, at this stage, the only ones that you should eliminate are ones that literally violate laws of the universe. So first law violators, second law violators, things that spontaneously generate or destroy mass, solutions that require time travel, telepathy. And I do require in 4501 that you actually do a calculation to prove to me that something is unphysical. And I've got a whole lecture on that, so we won't dwell on it. But at this stage, you do not eliminate concepts that fail to meet the customer needs, right? So a lot of these are either too big or too slow or don't have the accuracy range to meet the metrics that I set before. I do not eliminate them in this step. I do not eliminate them here. I eliminate them in step 7, which is down selection. I only eliminate truly impossible concepts at this phase. Okay, we're right at the end of time, so let me stop there. If I can answer any questions relevant to today's lecture, we'll keep recording and I'll answer those questions. Otherwise, you guys are free to go. So any questions? Jack is asking, are we able to pick up the lab kit today? Yeah, until 4:00 p.m. today. Noel will be there. The lab kits, I'm actually glad you asked. The lab kits are, let me close this and open this. The lab kits are sitting in the lab. We ran out of boxes. And so the lab kits are sitting in the lab on a bench. They look like this, and you might walk past this and think to yourself, oh, somebody set up an experiment or something, and I'm not to touch this. But these are actually your lab kits, right? So the flame tubes are in the blue boxes, the eyeglasses, the safety glasses are in the bags, and the calipers are in these sort of black containers. And then the ledger to sign out your lab kit is here. So don't get confused as you walk into the lab and walk past this thinking that this is for somebody else. This is set up for you guys. Um, Other questions?
I just have a question about the RER in general. I was wondering, are you going to give us like suggested milestones, I guess, of what we should have done by a certain time, or is it kind of up to us to like plan all of it out?
It's up to you to plan it all out, and that's what the Gantt chart assign. Well, okay, let me. So I used to have a separate Gantt chart assignment, which would have been due in the second week of class, where students were meant to like schedule everything out in advance. There was some feedback last semester about there being too many assignments in 4501. So I rolled the Gantt chart assignment into the RER. But if you read the details of the Gantt chart section, the suggestion is that you make the Gantt chart first before you do anything else. And then use that kind of as a measuring stick to keep yourself on pace to get finished in time. But I'm not going to provide any milestones or guidance. It's all up to you guys now to sort of set your own cadence for how you want to tackle the RER.
Okay, thank you.
Yep. Any other questions related to the presentation? I'm happy to stick around and answer kind of RER questions later, but I want to make sure that we stop the recording if there are no more relevant questions. Okay, so let me stop recording.